In this video, we're going to work with section 6.1, part 2. We're going to build and use the unit circle. At the conclusion of our work with 6.1, part 1, we had used a series of special triangles to build a series of points on the unit circle, all in quadrant 1. So I'll have you refer back to your notes there or the video that built these pieces. But we wound up with 5 points on the unit circle. A couple of them living at the poles, and then 3 of them just at the location of some of our special triangles. And so as we moved into section 6.2, I started you out, or 6.1 part 2, excuse me, you'll start with a blank note sheet of the entire unit circle. And what I asked you to start with is to just simply fill in, take what you had here, and put it into your quadrant 1. And so what you'll see, and I'll just kind of shade things off for a moment, in my upper right hand corner, I've taken everything that I had seen right here, and I've snapped it into quadrant 1 of the unit circle. In class, what we subsequently did, and we're going to save ourselves just a little bit of drawing time here, I had you we used some color coding, and we made a series of bow tie diagrams. Kind of see a red bow tie structure here, a blue one, and a brown one, or black, just depending on what color we're getting here off of our camera. We were able to use symmetry of our locations in quadrant 1 and apply them to quadrants 2, 3, and 4 to build the entire unit circle. So I'm going to focus on just the red segment very quickly. Here comes an entirely completed unit circle. And I'm going to look at quadrant 1 in red here. That's a 45-degree reference angle. And if I make the rest of my bow tie diagram, you'll see 45-degree angle, reference angle living in quadrant 2, 45-degree reference angle living in quadrant 3, 45-degree reference angle living in quadrant 4. And using our formulas, I can go ahead and identify those angles as 135, 225, and 315 respectively. Or pi minus pi over 4, 3 pi over 4, pi plus pi over 4, 5 pi over 4, 2 pi minus pi over 4, 7 pi over 4, for the radian representations of those 4 angles, in this case in quadrant 4. And what can I do with root 2 over 2, root 2 over 2, positive, positive in quadrant 1? What happens to the point over here, the terminal point? Well, the x-coordinate now becomes negative, the y stays positive. Negative root 2 over 2, root 2 over 2. Going down to quadrant 3, what happens? My x and y coordinates that used to be positive in quadrant 1, I now make them both negative in quadrant 3. And then finally, working over to quadrant 4, keep my x coordinate positive, make my y coordinate negative. And then we repeated this exact same exercise using 2 more bow tie diagrams, if you think about it. The blue version, the brown version, and we built all the other points on the unit circle. So I'll have you at this stage just freeze the video, stare down all the different contents, and you can see how this entire unit circle was built. One point also to come back on this. Knowing all these point locations on the unit circle, each one of those points is associated with an angle, and those terminal points are going to give us, these x and y coordinates are going to give us the trigonometric functions. We can use the y value as the sine, we can use the x value as the cosine. So again, freeze, stare down your video, understand all the terminal points that you see here in this, and we'll go ahead and continue in a few moments with the next part. So moving forward in our notes then, we started working on using our unit circle to solve a series of problems. So far, our unit circle only shows us so many things. It only shows us angles that live between 0 and 360 and 0 and 2 pi. But we can extend that very easily, and we can take other angles and identify where they live on the unit circle. And that's what we're going to do next. More terminal points on the unit circle. If you're not between 0 and 360 degrees, 0 and 2 pi radians, and by the way, most of what we're going to do today is going to be radians based. What can you do? Go coterminal. Once you're coterminal, you now have a terminal point that you can identify. So negative pi over 4 doesn't live on the unit circle, but if we add 2 pi, which is the same as what? Adding 8 pi over 4, I wind up at 7 pi over 4. And with my unit circle, what do I know about 7 pi over 4? It's in quadrant 3, root 2 over 2, excuse me, it's in quadrant 4, root 2 over 2, negative root 2 over 2. Continuing, 8 pi over 3. Well, 8/3 is bigger than 2, so we're bigger than 2 pi. I'm going to subtract 2 pi minus 2 pi. That's the same as 6 pi over 3. I'm going to be at the point 2 pi over 3. 8 pi over 3 minus 6 pi over 3 takes me to 2 pi over 3. 2 pi over 3 located in quadrant 2. What's my unit circle tell me? Negative 1/2 root 3 over 2. Negative 1/2 root 3 over 2. Negative 5 pi over 6. Negative angle, add 2 pi, which is the same as adding, in this case, 12 pi over 6. I'm going to wind up at 7 pi over 6. 7 over 6, a little bit bigger than 1, less than 1/2. I'm in quadrant 3. 7 pi over 6. Negative root 3 over 2, negative 1/2. And again, if we know the terminal point associated with negative 5 pi over 6, we know the trigonometric ratios associated with negative 5 pi over 6. The next thing we're going to cover is the concept of a reference number. We've been very familiar so far with our good old friend theta r, which we've always called our reference angle. And we're going to start to use new language today. And it starts with the concept that we've already said before, that we're going to start to use the letter t in the equation s equals r theta. We're now going to use t rather than s. So we will say our arc length t, which happens to be a travel along the unit circle, is equal to r times theta, our angle measured in radians. The beauty of the unit circle is the fact that r equals 1. And so what we're going to come up with now is that our arc length is going to be on the unit circle exactly equal to the angle that builds that arc. Important point. And so you're going to notice we're going to start using the letter T for our arcs rather than S. And remember, we always build a bow tie diagram whenever we travel along a circle. We're going to now have theta r, we're going to give it a new term. We're going to call it T bar. So T bar is a reference number or a reference angle on the unit circle. It's the same concept. It uses the same formulas that theta r did. So let's take a quick look in the different quadrants. Here's my arc T in quadrant 1. Angle theta builds that. Now we will call this arc T. The reference angle that lives right in here. Remember, you are your own reference angle. T equals theta, so we're going to call everything T now. The reference value is nothing more than what this angle T happens to be in quadrant 1. In quadrant 2, there's my arc. It goes into quadrant 2. There's my reference angle, T bar. T bar is equal to pi minus T. Why would you say that? Well, I come a little bit short of what? Doing a half circle, which is pi radians. How far did I fall short? By that little reference angle, that little bow tie angle. What's the measure of that reference angle? Pi minus T. In quadrant 3, hey, my angle goes what? Well, it goes a little bit past pi radians because it goes into quadrant 3. It goes past by how much? That little lovely reference angle. How big is that reference angle? T minus pi. And in quadrant 4, there's my big arc driving into quadrant 4. I come up what? A little bit short of going 2 pi radians. What's my formula? Reference angle. 2 pi minus T. 2 pi, the whole circle length, minus T, my arc length. So there's our reference angle formulas. Again, remember, T bar is no different than theta r that we've talked about for a long time. All right, so we're going to find the reference angle for each real number T. Just like before, A reference angle always lives in quadrant 1. When you know a reference angle, think about this. When we worked with our quadrant 1 piece, that was all our reference information. And we used all that reference information to do what? Build the rest of the unit circle, find all these different terminal points. We're going to do that same exercise very soon. So find the reference angle for each real number t. T equals 5 pi over 6 turns out to be an angle that lives in quadrant 2. I'm going to be in quadrant 2. What do I know my reference angle formula is? In quadrant 2, it's pi minus 5 pi over 6 equals pi over 6. 4 pi over 3 is an angle that lives in quadrant 3. 4 over 3 is a little bit bigger than 1. It's a little bit less than 1.5. That's why I know quadrant 3. What's my formula? Angle minus pi. Reference value is pi over 3. 7 pi over 4. That's 1.75. That's in quadrant 4. Reference angle formula, 2 pi minus 7 pi over 4. 8 pi over 4 minus 7 pi over 4. Reference value, pi over 4. Pi over 3. Lovely. It's in quadrant 1. You're your own reference angle in quadrant 1. That one was easy. 15 pi over 4. 15 over 4 is 3.75. That's a lot bigger than 2. I need to go coterminal. I'm going to subtract 2 pi, which is subtracting 8 pi over 4. 15 pi over 4 minus 8 pi over 4 gives me 7 pi over 4. And what do I notice? I can use my answer in part C. I'm in great shape. 15 pi over 4 and 7 pi over 4 are coterminal. What's my reference value? 2 pi minus 7 pi over 4. And again, I'll walk into pi over 4 just like I did in my prior problem. T equals 5.80. This one's a little bit tougher. Why? Or a little bit surprising or a little bit unfamiliar because it's a radian value, but it doesn't have any radians in it. So how can I figure out where this lies? Well, we're going to use our calculator. And here's what you'll find out. Get it turned on. Let's kind of figure out how big is 2 pi radians as a decimal. So I'm going to do 2 times pi. I find out I get 6.28. So I know 6.28 radians lives right there if I go a full circle. Let's check down here, which is 3 pi over 2. 3 times pi divided by 2, 4.7. So 4.7 radians is a good representation of 3 pi over 2. 6.28 is a good representation of 2 pi radians. What's that telling me? 5.8 radians is in quadrant 4. And what's my formula? 2 pi minus 5.8. 2 pi, 6.28, minus 5.8. My reference value, T bar, is 0.48. Now, 0.48 radians doesn't show up on the unit circle or whatever. That's okay. Reference values are legitimate no matter what, whether there's a pi floating around or not. These are all radians. Formulas always apply. Now, the nice thing is, again, when you find a reference number, you found the quadrant 1 partner that would go with your angle. So, for instance, let's take a look. 5 pi over 6. What do you notice? Its reference angle is pi over 6. Look at that. Pi over 6 right here as well. They are partners on the unit circle. And that tells me if I know the coordinates of the reference angle, root 3 over 2 1/2, I can apply those coordinates to the other quadrants, changing the sign as appropriate. So if I know root 3 over 2 1/2 here, the companion in quadrant 2 has to have coordinates negative root 3 over 2 1/2. And we're going to use that knowledge to work the last part of this lesson. So here we go. We're going to be asked to find reference angles and terminal points for a series of angles measured in radian. Step 1, we're going to identify the quadrant where the angle lives. Step 2, we're going to get the reference number. just like we did on the prior page. Step 3, we're going to find the terminal point of that reference angle in quadrant 1. And step 4, based on the quadrant where our angle has been identified to live in, we're going to take the quadrant 1 coordinates and apply them to our quadrant. So let's go. T equals 11 pi over 6. That is located in quadrant 4. I know, by the way, that x is positive, y is neg in that quadrant. Reference angle, 2 pi minus 11 pi over 6 equals 12 pi minus 12 pi over 6, minus 11 pi over 6, pi over 6. I know that when I look at my quadrant 1 unit circle that pi over 6 is located at root 3 over 2 and 1/2. Where do I need to be? I need to make my x-coordinate stay positive, root 3 over 2. My y-coordinate becomes negative 1/2. And we can check our drawn unit circle. Look, there's 11 pi over 6. And what do you notice? Root 3 over 2, negative 1/2. Now, what we're doing here presumes that you only have the first quadrant of the unit circle drawn. Obviously, we have the whole thing drawn, so we can kind of figure out the answers. But if you really think about it, what we did here was really not much different than how we used the quadrant 1 information to go ahead and build the respective partner values in quadrants 2, 3, and 4. Same concept. I knew my location, point location here. I could find a similar reference angle down here, change my y-coordinate, make it negative, keep my x-coordinate positive, and all was fine. But again, if all we know is quadrant 1, we can use these reference values and very quickly find terminal points on the unit circle for other angles. 5 pi over 4. 5 over 4 is a little bit bigger than 1. We're going to be in quadrant 3. My x-coordinate is negative. My y-coordinate is negative. My reference angle is 5 pi over 4 minus pi. 5 pi over 4 minus pi. That's going to be pi over 4. I know in quadrant 1, pi over 4 is what? Root 2 over 2, root 2 over 2. In quadrant 3, both things are negative. Negative root 2 over 2, negative root 2 over 2 is my terminal point. T equals 2 pi over 3. That is a quadrant 2 angle. It's a little bit, 2/3 is a little bit bigger than 1/2. It's less than 1. In quadrant 2, x is negative, y is positive. My reference angle, pi minus 2 pi over 3, that's my quadrant 2 formula, gives me pi over 3. What do I know about pi over 3's coordinates? In quadrant 1, it's 1/2 root 3 over 2. 1/2 root 3 over 2. I need to make my x negative. Negative 1/2. My y stays positive, root 3 over 2. Negative 1/2 root 3 over 2. A few more problems to go. Negative 7 pi over 4. Go coterminal. In this case, I'm going to add 2 pi. That's the same as adding 8 pi over 4. Negative 7 pi over 4 plus 8 pi over 4. Reference angle is pi over 4. Excuse me, not the reference angle. The coterminal relationship, value on the unit circle, is pi over 4. This is a quadrant 1 angle. By the way, what's the nice thing about quadrant 1? You're your own reference angle. Pi over 4's reference angle is pi over 4. Its terminal point is root 2 over 2, root 2 over 2. 2 more to go. T equals 10 pi over 3. 10 thirds is 3 and 1/3, 3.3. It's bigger than 2. Go coterminal, take away 2 pi, which is the same as taking away 6 pi over 3. And I'm going to wind up with 10 pi minus 6 pi over 3. I will have 4 pi over 3. 4 pi over 3, we did a little bit before. It's located in quadrant 3. X is neg, y is negative. Reference value, 4 pi over 3 minus pi equals pi over 3. Again, what do we know about pi over 3? It's located at 1/2 root 3 over 2. 1/2 root 3 over 2. I need to make both of those negative. Negative 1/2, negative root 3 over 2. Last problem, negative 19 pi over 6. We got to go coterminal. That's a negative number. Let's add. 2 pi is the same as adding 12 pi over 6. That would take us to negative 7 pi over 6. Still not positive. Going to add again. And what would happen there? Another 12 pi over 6. I'm going to land at 5 pi over 6. 5 pi over 6 is located in quadrant 2, where x is negative and y is positive. So I'm in quadrant 2. 5 pi over 6 is a good coterminal representation. Reference angle formula. Pi minus 5 pi over 6 equals pi over 6. Unit circle tells us pi over 6 has what? Root 3 over 2, 1/2. Make x negative. Negative root 3 over 2. Keep y positive, 1/2. And there's my terminal point. Again, all the nice things that will come out of this is these terminal points, these x and y coordinates map perfectly. The x coordinate maps to the cosine of your angle. The y coordinate on the unit circle maps perfectly to your sine of your angle. So there's the unit circle, constructing it, building it, identifying reference angles, reference numbers, using that to identify terminal points, which in turn we're going to use in our next lesson to identify the trigonometric functions. So that concludes this lesson.